Hello. Okay, so let's get started with some of the hints for the problems. I don't remember what came after the hypodermic needle question, so I've left that, left anything after that. But let's go through the problems one by one. The first one, I'm pretty convinced your professor who said you wanted to use, you were supposed to use um, impulse. Change in momentum is, I think that's a bit of overkill. He might be right. You might be able to get to the same answer, but I've been trying to look at some of the resources online to confirm or deny my suspicions, and it seems like what he's suggesting is overkill. The approach, and I'm sure I think we went over this just to confirm. I did this separately, not remembering what the values are. The change in velocity over change in time, we know we're going from 80 kilometers an hour to 0 in 5 milliseconds, which is a really short amount of time. So that is actually a deceleration of about 4 kilometers per second squared, which is massive. So the stress, if you do your calculations, should actually end up being fairly high up there, but not as much as what is given as the failure point, which is 16, and you have 5.5, and therefore your bones will not compress sufficiently enough to cause failure. So hope that helps. Let's take a look at the second question. The second question involved the Marianas Trench, I think. And this one is a scenario in which you have a block that is at a particular at the surface, and we want to know what happens to it when it goes 11 kilometers down south beneath the surface. We're told about the pressure at the bottom. And we also know implicitly what the pressure is at the top, and we also know the distance. Do we need to know the distance? I don't think. Let's see. So the equation that we want to use is the bulk modulus equation. Basically, we're saying the change in pressure and the change in volume is going to be proportional to a constant that is related to the initial volume as well as the property of the material. Let's see, so we have, yeah, you don't actually need to know that it's 11 kilometers. You have the surface pressure, which is 1 atmosphere. If you take a look at 9.5 to pull up those numbers, but I think this is correct. The bottom pressure is given in the problem, and you want to use B as your 0.21 based on the table in the early parts of the chapter. This is the value for water, but I wasn't particularly satisfied with it, so I looked up what the value is for seawater, and it turns out to be fairly similar. So since it doesn't give you, they don't give you the value in the table, I would say that you could use 0.21 times 10 to the power 10, but you could be super accurate and use the slightly higher value of seawater. The volume is 1 meters cubed, and so I haven't solved this one out, but you basically want to find the change in volume, given that you know what B is, you know what the initial V is, and you know what the change in pressure is. Basically, it's going from a fairly small pressure to a higher one, right? The second part of the question asks for the density. Density is mass over volume, and we just calculated what the change in volume is, and therefore you can find the density at the bottom and use that as a measure of compressibility for seawater. Let's see, the follow-up question to that is going to be on the tallest cylindrical pillar of cement. And I'm just going to cut this so that it actually fits. The problem tells us that we're to find the highest height for a volume of cylinder of cement, such that it does not collapse on its own weight. Let me make sure I have that question correct. Right, so we're actually not told that it's actually a volume of 1 meters cubed, but we are told that if it has a volume of 1 meters cubed, it weighs 5 times 10 to the power 4 newtons. The compression strength for concrete is this particular value. What helps a lot for me is actually to decompose these units, because pascals means pressure, but if we can decompose this into something that makes a little more sense for us, it would make a lot of the calculations easier. And in this case, we're doing Pascal is newtons per meter squared, which basically says that you can apply this amount of newtons over a single meter surface of 1 meter squared before it starts breaking. It's a little hard to visualize because any real material we have has to have a certain amount of thickness, but we can then sort of think of compression strength as nonetheless a ideal property of a material that says that if we were to have a square surface of 1 meter squared, then it could take 1.7 times 10 to the power newtons applied to it before it breaks. Very idealized, hard to visualize, but certainly the general idea behind that. And so what we have to do is now find the height for which it does not compress, does not fail. And basically that's saying that if we were to use the bottom of this particular thing, a really small height of this, right? If this was to support all of the mass above it, then how high of a mass of concrete can we say, or can we use before things start crumbling based on the compression strength of concrete? And so we have to find the mass, we have to find a height for which the mass of the concrete above the base is going to be equal to 1.7 times 10 to the power 7. And so the general question that you want to answer in solving this question is how much concrete will weigh 1.7 times 10 to the power 7 newtons. And I'll leave you to solve that. And I think the next question is going to be on the hypodermic. No, actually, it's on the brake shoes. I apologize if I get this wrong in order. But we have a scenario where we are working with a brake shoe that someone is applying some sort of pressure on the pedals, and we're asked to find the rotational torque applied to the brake pads. Let me make sure I read that correctly. What is the frictional torque about the axle when a force of 44 newtons is applied? In order to go about solving this, we sort of have to imagine that we have a wheel here, and we have the axle, and this entire system sort of is a zoomed up version of what's happening here, such that there is friction applied to the edge of this, and we're being asked about that frictional torque. If something like this comes up on a quiz or a test, one of the things that happens a lot for me is I freeze up and I'm like, I have no idea what they mean by frictional torque. I would go about saying, okay, I have no idea about frictional torque. What do I know? What can I solve? Are there keywords that I can use? Are there equations I can use that potentially then make sense about what this is? And so for me, at least, it helped because this one was a little tricky. So let's first list out what we know. We know that the applied force here is 44 newtons. So your feet is applying a certain amount of force. We also know that the radius of the wheel is 34 centimeters. We also know that the coefficient of friction is 0.5. And we're given sort of areas and surface areas and for each of the master cylinder and the brake cylinder. One of the equations that's going to be particularly useful here is the continuity equation. It's actually the first part of 9.7, which I'll cover the rest of in a bit. But the continuity equation basically says that, let's see if I have a, yes, actually, let's take this for granted for now, and then I'll try to explain the derivation for this in further detail. But this equation is what's going to be key here, because it's basically saying that the velocity of a let's see, that the velocity of a fluid, actually this one's, sorry, I apologize, this actually is not going to be useful. We're actually going to be using a variant of this equation, which is Pascal's principle. Let's see if I can pull up the page where it is on my textbook. Yeah, it's slightly before the. I can't pull it up, but basically the idea behind Pascal's principle is that if you have a closed system with a varying cross-sectional area, the forces, the pressure in one spot has got to be equal to the pressure at another spot. And so this is a fundamental property of liquids. And basically, if you decompose that into, so this is equal to P1 equals P2. The reason why you can have, so the reason why this is important is because even though the pressures are going to be the same, the cross-sectional areas could be different. So if you decompose that, then you're basically saying that the force that is applied right here is going to be following this particular principle related to the force applied here, which sort of makes sense, I think. If you imagine yourself pushing on here, you would expect there to be a sort of equal distribution of that force spread out over, if this were larger, over a larger area, right? Liquids don't, we're assuming here that liquids are ideal, and I would definitely make sure that those assumptions are very, very clear here, but that means that the amount of force applied here is going to be distributed regardless of where it ends up. So if we were to use Pascal's principle, we can then now find what the force is right here, right? Because we know what F1 is here. We know A1. We know A2, and therefore we can find the force applied here. And if you do find that force, let's leave it at that. Let's say you got to that point and you're saying, well, this question gives me force of the coefficient friction. So there's some friction force force that we're going to have to calculate. What's the one equation that comes up to mind when you're given this? Usually a lot of these problems end up being, I'm given this, what can I use this for? So the main equation here is the frictional force is going to be mu sub Fn, right? So the coefficient I've written right here. So if we harken back to the earlier chapters, the frictional force is a force that counters the direction of motion with magnitude equal to the coefficient of friction that defines how rough a particular surface is, and the normal force, which is also related to the I guess the mass, it's the opposite of the force due to gravity unless there's other forces being applied. And if you were to turn this around, we have just solved for what the normal force is. In this case, it's actually going to be in the opposite direction, but we are essentially working with a particular force that is applied perpendicular in a microscopic scale. Obviously, we're actually looking with a surface that's a little curved, but we're dealing with a force that's applied perpendicularly to a small spot on the wheel, and we are told about the friction coefficient on the brakes, I guess. And so essentially, we're now asked to determine what amount of force if we were to apply that, how much frictional force is being generated as a result. And if we do know that there is a frictional force, we also can go back and say, well, I don't know what frictional torque may mean, but I know that torque is actually going to be a value related to where there's a fixed point, and if you apply a particular force in a particular direction, it's related to the distance and the magnitude of the force. So torque equals Rf. And this should also be one of your equations. And if you then draw your wheel around it, you basically are being asked for what torque is given the radius and given the fact that you just solved for frictional force. This may come across as a little bit of like a kludge where I'm like working backwards because I know the solution, but I think the general idea is to, proceed with what you have. So you know that you have different surface areas, and therefore you need to start relating one side to another. And you also want to lay out the equations for particular keywords that you know, specifically torque and friction. So given that, the torque, and I haven't solved this myself, but the torque is going to be force of friction multiplied by the radius, where the force of friction is going to be mu f, so your coefficient of friction times the normal force, where the normal force here is actually F2. So moving right along, we're going to talk about fluids in motion. So we're working with fluids that are moving. Once again, we're working with ideal fluids. Let me recap what those are, what that means. It means that there isn't actually friction within the liquid, so that's number one. The fluid is non-viscous. We're talking about the fact that the fluid is incompressible. So the earlier question about the Marianas Trench and seawater, that was a scenario where the fluid is actually compressible, and therefore it's non-ideal. We're saying that the motion is steady, so everything is not accelerating. It's basically velocity doesn't change, density doesn't change, pressure doesn't change. This is specifically for fluids in motion, right? So when things are moving, we don't want to make things too complicated. If you do like making things complicated, I would talk to Susie, who's doing something similar in this domain. And then number four, fluid doesn't move with turbulence. So turbulence would create basically a situation where fluids are colliding with each other, and you would have a whole mess of things. So there is an actual, if you're looking at fluids in motion, we're not saying that there's little bits of fluid that's like sort of tumbling about on itself. As in all physics problems where everything is pretty idealized, so that this assumption is going to hold pretty much for any fluid in motion question. So let's look at a scenario where we have a tube, and the tube is fairly narrow at one end and fairly large on one end, on the other. we don't necessarily need to have this going down or up. It will come in handy when we take a look at Bernoulli's equation, but it really doesn't matter if this were just a tube that's horizontal. If you're familiar with Swiss instruments, and I know I should stop with the pleasantries, but there's a nice Swiss horn thing, and Bernoulli is Swiss, so I kind of like drawing this. But basically, what we're going the first of two equations that we want to deal with is the fact that we have a sense of continuity between the fluid here and the fluid here. That is, nothing is evaporating, nothing is disappearing, nothing is changing between these two. Therefore, we can also say that whatever comes in must also come out. And if we sort of make a very formalized version of that, we're saying that the mass of whatever is coming in is also the mass of the water coming out. Nothing is disappearing along the way. So we're saying mass that flows in must also be mass that flows out, because nothing disappears. Right? So if we go about deriving that, then we know that mass is the density times volume, right? Density equals mass over volume. So if we have mass, we then say density. So let's just take a look at the top scenario here, where everything is, we're dealing with things that are going into the tube. Then the density times volume is going to be, we're going to say, okay, that's the mass going in. And the volume is going to be the cross-sectional area times a small delta x. Obviously, we're in this scenario, we're sort of seeing a tube that sort of snakes and changes potentially so that delta x doesn't really have meaning, but on a very microscopic scale, if we had a cross-sectional area, we would also expect there to be a delta x that defines how deep that is, right? Because then we can, if we have that, then we can define, it's almost a height basically of a cube or width, where a1 delta x is going to define the volume. Right? So if we do that, then this delta x ends up being sort of an assumption, right? We can't guarantee that delta x is going to be linear, but it helps us in the math. Then if we substitute that in, we know that delta x is also v delta t because of the equation for velocity. And that helps because we know that for any set amount of time, the mass that goes in is going to be the same as the mass going out. And so as a result, if we set those two together and substitute the velocity, we can then strike out delta t, because delta t in equals delta out. We can also strike out yes, we can strike out another thing, the fact that the density is not going to change over time. So in essence, our final equation is basically A in, V in is going to be A out, V out, which was the equation of continuity that I had earlier. So this is in contrast to the F1 over A1 equals F2 over A2, which relates pressures along the way. Here we're saying the velocity is going to be related to each other by a ratio that is relevant to the cross-sectional area. Neat. And if now, so to make things even more complicated, right? If we're looking at fluids in motion, if things are moving, we also have work that we need to consider. And so Bernoulli's equation helps in this. So if we now, I'm going to invert this just because it makes a little more sense. I got myself a little confused actually when I inverted the tube so that it's going downwards like I had earlier. So I would make sure that the directionality and the work makes sense. If not, I would bring it up with your professor because I'm a little confused myself. So in this scenario, what we're doing is we're going to now define work. What is work? Work is force times distance, right? And we go ahead again with that same assumption of what the distance is, where the distance is the amount of the distance required to move a fluid by a small set distance, delta x. And we also know what the force is going to be. The force here is going to be, because pressure equals force over area, right? Force equals pressure times the cross-sectional area, as I wrote right there. And as a result, then work ends up becoming P1A1, which is force, times delta x. And this A1 times delta x is going to be the volume, which is exactly the same thing what we said earlier, right here. And if we do the same for the things that happen at the top, we know that the same rules apply. The point here I want to harp on is the directionality of work. I haven't been able to get a satisfactory explanation as to why it is. The textbook sort of says, well, if we're at the top, the force applied from the fluid is such that it's going to try to push it back, and therefore it's opposite to the displacement if the fluid is being pushed upwards. I found that to be a woefully inadequate explanation, but that might work for you. And so if we were to say, what is the total work? The work done by the fluid is going to be work here plus the work here, where it's going to change simply because there's actually a change in height. And so then if that is indeed the case, then if we sum those, that's going to be a difference, P1V1 minus P2V2. And this is going to be equal to the change in kinetic energy plus the change in potential energy. Let me make sure that also, so if we were to write this out, 1/2, so kinetic energy is going to be 1/2 mv squared. So let's say that's 1 m1v1 squared minus 1. So the change in kinetic energy is actually going to be the kinetic energy here minus kinetic energy here. I have a suspicion, actually, going back to the negative, that this is going to be W2 minus W1, and the mathematical derivations of those are going to work out. I could be very wrong, though, so let's scratch that. So here we have 1/2 mv2 m2v2 squared minus 1/2 m1v1 squared, right, plus the change in potential energy. And we went over earlier the fact that this is mg h minus, so h is going to be actually y2 minus mg y1, where y1 here. And so we're sort of imagining our water molecules to have a discrete volume and mass such that we could almost translate this exact problem into what would be happening if we moved a box from here to here. And we were doing it with a particular speed. So if there is a change in potential energy there. And there's going to be change in kinetic energy potentially because things are moving in a particular direction with a particular amount of speed. And so what Bernoulli found out is that then if we were to write this out, basically the using the continuity equation, that P1 plus 1/2 rho V1 squared plus the rho G1 rho G Y1 is going to be equal to the pressure at the second point. The sum basically of this is going to remain constant. And the so if you look at things in terms of so if you made things a little simpler and said what would happen if you had a tube that sort of narrowed down at a certain point, the Bernoulli's equation says that at every point along this streamline, if we know what A1 what the cross-sectional area is, we can also find the velocity at a particular point, and we can also find then, actually, if we have the cross-sectional area and we know that a particular amount of force, we can find pressure, and in general, this particular sum is going to remain constant at any point, right? So some things may go up where other things go down. And this is actually going to be helpful in the hypodermic question, hypodermic needle question. Let's see if I have that. So I actually haven't drawn it out, but in solving the hypodermic needle question, it's exactly almost a parallel of this, it turns out, right? We are given the cross-sectional area here. We're given A1. We are also given what the force is, right? So we are given force. So this ends up being a very, very similar analog to the brake pad question. We are also given A2, right? Yeah. Barrel of syringe. We are not given A2, but we are told that the pressure remains the same throughout the needle, so that we know what the pressure here is, and that's going to be equal to the pressure here. So P1, we can calculate what P1 is. That's going to be equal to P2. Yeah, I think you should be able to solve this. I may write this out and do another video, but I would try solving it using at least Bernoulli's equation. We also know here that if the syringe is horizontal, there is no change in y, and therefore we can knock this out.